Good evening. Good evening, everybody. Thank you for coming. I'm Michael Walker. This is the Data Science Association. It's July 14th, 2014, and today we have an event entitled In-Memory Computing Principles. I'd like a show of hands. How many people are working with in-memory databases? Quite a few. How many are working with Datagrids? How about Hadoop? How many are working with Hadoop? Okay, very good. I just want to remind all of you, we have free membership for a year with the Data Science Association, and I'd urge you to join up. We have a lot of wonderful resources. We have different committees that we're asking for volunteers to join. Marilyn heads up the committee to plan the big data science conference. We're looking to plan that for spring of 2015. Michael Malik heads up the committee for education and curriculum. And there are other committees there that I'd like you to check out. We'd love to have you volunteer for them. Also, if anybody is interested, we're looking for more bloggers. If you want to do a paragraph or two or blog once or twice a week, please check out some of the blogs. I'd like you to consider coming and blogging. I'm really pleased today to have a new sponsor, GridGain. And GridGain is an in-memory computing company. I have a chance to get to know Mac and Cordero and some of the other people at GridGain. They're really good people. They're really knowledgeable. They're just good people to work with. And I'd like to turn it over to Cordero, and then Cordero is going to turn it over to Mac.
Hey, good evening, everybody. As Michael said, my name is Cordero, and I work for GridGain. Really want to thank Michael and the rest of you guys for coming out tonight and hear our presentation. You know, this isn't intended to be a sales call in any shape or form. This is about educating the people that matter, and that's what we believe you guys are. The intent is to get the word out there, people talking in memory. I mean, you guys have probably seen the analytical reports talking about in-memory technologies and the need they have for transaction, real-time analytics, accessing data faster, whatever. And that's really what we're trying to focus on at GridGain is real-time data access and performance. So it doesn't necessarily why you guys are, you know, the big data space doesn't necessarily have to be that. We have, you know, people that are using our technologies that have relatively small sizes of data, but it's about data performance at the end of the day across the board. So again, the hope is that we, re-educate you or maybe re-familiar with what's the latest and greatest in the space, and you guys are out there talking with people that matter. If there's any in the future, should there be desire from any of you to maybe replicate this or talk to specific people or you'd like more information, all of my contact information's up here, so feel free to do that. If you didn't register for out there for the Jambox, please do that because I will be compiling and the random generator will be pushing out the email to the person that's going to win before the end. You need to be present to win, and that raffle will take place probably 30 minutes after Mac is done with his presentation. So if there's no questions for me, again, I just want to thank you guys for being here and for taking the time to listen to this. And Mac here is one of our senior solutions architects on the team. He's been working in the in-memory space for a good chunk of time now. What makes Mac even special, he's a consumer of the technology as well. So he comes from a corporate entity that was using in-memory technologies, went out doing research, why we needed it. He brought it in, and now he's actually architecting environments. So with that, it's all yours, Mac.
Thanks, Cordero. So let me echo the sentiments in terms of thanking you guys for coming out. Nice to meet everyone, or actually I haven't really met you yet, but you'll get to know me a little bit during the talk, hopefully, and I hope some of you will stay after and we can talk a little bit about what you guys are doing, because for me that's really the fun part of this, is getting out, meeting folks, understanding the problems that you guys are solving. You know, to me, technology is fun and wonderful in the service of solving real problems, right? You know, I'm not one of these technology for technology's sake guys that just love something because it's new, right? I love something that can solve a real problem. And I think we're seeing more and more of that, obviously, within memory. I think there's a greater awareness of it. Obviously, some of you folks here are already working with it. So we're going to kind of set a baseline and then talk a little bit about sort of my take on how I think things have evolved, which is pretty interesting. As Cordero mentioned, you know, my background was in corporate IT and running development teams and building applications, and I became a consumer of this technology. I've worked for a couple of companies in the space, so been at this for a few years. Of course, it's rapidly evolving and rapidly changing. In fact, I think it's a difficult time to be a consumer of this type of technology because there is so much evolution and so much change. But at the same time, it makes it very exciting. You know, if you're like me, you work in technology because things do change, right? We like to learn, we like to evolve, and again, to me, that is what makes it fun. So, with that preface, and I guess one other thing, so if, and as we go through here, right, if you have questions, if there's something that you're just dying to know, please feel free to jump in there. We have dedicated Q&A time at the end, but, you know, I would probably say as a rule of thumb, if you're kind of going, I have no idea where you're going with this, I'm not following you, you know, jump in there, raise a hand, or shout something out. You know, if it's making sense but you just want to know more, we'll have time at the end to go deeper, and in fact we can make as much time as we need for that. So, what we're going to cover today, I'll try to stay over here where the camera is. We're going to do a little overview, why in-memory, right? Why does it matter? Why now? We'll talk a little bit about some use cases, and I hope as we talk about that, you may sort of have ideas about how it relates to what you're doing, and again, I'd love to hear about that afterwards. We'll talk about some different concepts and different approaches to sort of solving the challenges of performance and scaling as our data sets grow. And then we'll talk about specifically GridGain's approach to those challenges and what our products do in that space. So let's begin at the beginning, right? Why in-memory computing? So in a nutshell, it's about speed, right? It used to be that if you compared the performance of just getting data off of a spinning disk versus getting data out of DRAM, it was a few hundred times faster. Well, with today's architectures, from the hardware perspective, you're talking a few thousand times faster. And that certainly can only improve over time. What are we doing in the meantime, right? We're doing all this cloud-based stuff. We have the SaaS model. We have mobile computing, right? We have the coming Internet of Things. And of course, big data analytics, which is what we're probably all focused on here tonight. So all these things are going on. It drives you towards a need for as much performance as possible, and that drives you towards in-memory ultimately. So the analysts, folks like Gartner, folks like Deloitte, not known for saying things like, you know, disruptive and radical in every press release, but they're saying some pretty impressive things about in-memory. You know, long-term disruptive impact, right? Massive potential, future of computing. In fact, Gartner goes a little bit further. In a report that they put out last year, they went so far as to say that folks who are not taking advantage of these technologies are effectively at a competitive disadvantage. So, powerful statements, right? Obviously, huge trends at play here to sort of elicit that type of response. Let's begin with what we know. So, it's rather cliche probably now at this point to say data volumes are growing. These are some fairly recent numbers that are pretty interesting. It's like all data created and shared on the internet in zettabytes, which is pretty staggering. So okay, we know that, right? Data volumes are growing. The other thing that probably most of you know is memory continues to get cheaper and cheaper, right? So it's declining year over year, 30% or more in some cases. And all those things on the left are driving us to the performance that's becoming affordable, and we're seeing that reflected in the trends of technologies that folks are looking at. You know, in-memory databases, Datagrids, Hadoop. In fact, I expect the Hadoop piece, if we looked at it now, to be even bigger than what's reflected there. So to kind of sum this up a little bit, let's do a top 3 reasons for in-memory computing. First, the tongue-in-cheek version, right? Performance, performance, and performance. It's all about performance. It's all about speed. But, you know, let's think a little bit deeper here and try again. Performance, yeah, we got to keep it. Scalability kind of goes hand in hand, right? If I have to scale and process larger and larger data sets, I need better and better performance to answer the same questions in the same amount of time. And then number 3, future-proofing. So what do I mean by that? Well, it's sort of an outgrowth of the first two in the sense that if I can perform and I can scale, I can grow over time, right? So I'm future-proofed in that sense. But also in the sense that it's sort of transformational. You know, if I can answer a question in anywhere from minutes to sub-second time frames that maybe used to require an overnight batch process to answer that question in hours, that's transformational, right? You know, if I can put a dashboard in front of somebody, and if I'm, you know, running an e-commerce site, what am I selling right now in the last hour, the last 30 minutes, you know, as opposed to yesterday? That's very useful information. So what's the basic concept? And we're going to go deeper into this, but if you think about traditional computing, you know, all our data was in databases, which were disk-based. What was actually in memory, right? Just your application code, essentially, and a little bit of data, and that's all you could fit in an application server, and that's kind of the way it was for a long, long time, and that's just the way we did things because you didn't really have the option to have a lot of memory for your application. So the concept of in-memory computing says we're going to kind of turn this on its head, and we're going to put all of our important business data into memory, right? And the disk, or the disk-based database, is still there. In most cases, it doesn't go away. You know, there's great tools and processes that people have built up around relational databases over the years. It's great for persistence. It's great for recovery, for historical archiving, all that kind of stuff. So that doesn't go away, but it sort of becomes less important, right? I want all my working set of data in memory. And more importantly, as I need more, I'm just going to add more boxes, right? And that's a key point as well. So that's sort of the paradigm shift, and everybody is sort of at a different place on the continuum of, you know, how comfortable we are with this transition. Some folks have been there for years. Some folks are still kind of like, I don't know about this. It's kind of a brave new world, right? So we'll dive a lot deeper into how we do that and what the considerations are. But before we do that, let's think for a minute about use cases. So here are some examples. Again, I hope you have some more that we can talk about later. But if you think about the financial space, for example, kind of an early adopter of this type of technology, if you think about doing things like processing real-time market data. So I am a large bank with a large trading operation. I have hundreds of portfolio traders. Maybe they have a few thousand portfolios each. I have customized risk algorithms that every time the market ticks, I want to know the total upside and downside for every portfolio. So I'm recalculating every trader's positions across all these different portfolios, right? Every tick. You can't do that without inmemory, right? That's the kind of thing that just pushes you right there. You got to do it. Similar use case in fraud detection, right? So I'm swiping a credit card, or maybe nowadays I'm paying for something with my cell phone or with an app. Somebody has to make a decision. Is that really me? And is this a legitimate transaction, right? So how much time do you have to do that? I'm standing there swiping a card or holding up my cell phone to the scanner at Starbucks, right? A couple seconds, right? So those are big use cases. Again, that sector's been kind of early adopters of this stuff. Similar challenge in online and mobile advertising. You know, again, somebody's on a mobile device, or maybe they're on a website waiting for the page to load, waiting for the app to load. It's your job to figure out what ad to show them, or maybe if you're running a store, what products you want to advertise beside the one that they're actually looking at. How much time do you have to do that? Again, maybe a second, maybe less. So you can see some of the themes emerging here, right? A need for real-time performance, high velocity of data, sometimes high volume of data. You know, as Cordero sort of hinted, it's not necessarily about size. You know, you can put hundreds of terabytes of data in memory today if you want to, but if you only have a few gig, but you've got to have that data in sub-second time frames, you know, it doesn't really matter the size. And then the other thing that we're seeing increasingly, you know, again, in the online and mobile space, backends, obviously everybody whose app is tied to a service or whose game has leaderboards or has a multiplayer aspect, right? They have backends with very, very strict SLAs that they have to meet. And this sort of pure analytics play is something we're seeing more and more. You know, everybody's talking about the customer 360 view nowadays. It's kind of similar in some ways. Again, if you think about the theme, you know, I've got customers interacting with my company all the time through the traditional channels like call center and IVR, through the website, through mobile applications. And what a lot of people want to do nowadays is kind of aggregate that all together, look at it in real time as essentially sort of a streaming use case, build a customer 360 view, be able to identify people that have sort of strayed from the path or fallen out of a path that's going to make them successful and be able to somehow remediate that. There's also applications you can imagine in the sciences, the life sciences as well as others. Not probably a whole lot more that we have to go into about that, but you can imagine, you know, these are just sort of some of the highlights, you know, sparks some thoughts. And again, I would love to hear some of the things that you guys are working on later. So we'll talk a little bit more about that later, but with that little bit of sort of context out of the way, I wanted to present sort of an evolutionary series of steps, as I see it, that have kind of brought us to this point. If you think about traditional architectures first, right, the things that we're all used to and we've been building for years. You know, you may actually have the sort of three-tier pattern. You have web servers and app servers, or you may have a user-facing app server and a service layer. But you can kind of distill it down to some app servers and a database, right? So in this model, think about how we access our data. You know, it's something we take for granted. We don't think about it. But in the context of how things are going to change, it's important to take a moment and consider. First of all actual processing, all real work happens on the application server in most cases, right? Now, yes, some people would put a lot of business logic in stored procedures, but that's not the common scenario that at least not that I've seen. Wouldn't be my preference. So what are we doing, right? We're getting relational data from the database. It's ultimately all in disk, so we have to wait for that latency. There may be some amount of caching in there. You know, databases have had that stuff for years, and supposedly recently they've gotten really serious about it. You know, I think they're doing better, but we'll see. But the point is, I'm going out getting relational data, usually off disk, and I'm shipping that data across the network back to my app server. I then have to marshal it into objects, because we're all writing, you know, Java or C++ or C#. It's object-oriented stuff. So I create objects, I use that data, and if I need it later, I do the same thing again, right? So pros and cons, right? It's familiar, it's what we know, that's all well and good, but the database is essentially our central bottleneck, and it's somewhat wasteful in that we have this impedance mismatch between object data, relational data, we're marshalling back and forth, and we're doing it repeatedly. Okay, so let's go to the next step. So the next step, for some people, was to horizontally scale the database. So how does that change things? Well, it doesn't really. It means I can add a couple more servers here. Scalability gets a little bit better, but it doesn't change anything else that we just said. Now, this is typically seen in the analytical space, things like Vertica or Netezza, which happen to be very, very simple. That's the other big downside here. So these are somewhat rare birds and very expensive. You're not going to see this in small to medium-sized shops for sure. So what's the next step, right? So for a lot of people, it was sort of the classic distributed caching picture. So now I have a standard relational database, Oracle SQL Server, MySQL. I added a distributed caching product, right? So the nice thing about this is, first of all, I'm not bound by disk anymore. I have data in RAM. I have it on multiple servers. And I can store it in objects, right? So most of these products are key value stores. The keys and values being objects. So those value objects can be essentially your business object, or can be some custom object that you've designed to represent your domain model in a way that makes sense for your app. So I can store object data in RAM. I can ship it across the network to the app server. This all makes a lot more sense, right? And you typically do this. We have our cross lines here, but you typically do this in sort of the cache aside pattern, which means the reason it's aside is, and the reason the database and the cache are side by side is, the idea is look at the cache first. If I have the data, I use it there. If I don't, I go back to the database, create it, and put it in the cache. So that's kind of your classic, again, cache-aside or standard caching type pattern. So this is great. Performs much better, getting data from RAM, storing it in objects. I don't have that impedance mismatch. I'm still sending across the network a lot of data, though. That's not ideal, but it's still obviously a big improvement from where we've been. And of course, these products tend to be much more affordable. They run on commodity hardware, etc. So this is great. Let me show you, I'm not really ready to talk about our product specifically, but I'm going to show you our kind of take on this, which we think is the next step, and then I'll talk more a little bit later, a little bit more detail. But now we can actually, with GridGain, do all that distributed caching stuff that I just talked about. In fact, you can use us in exactly that picture if that's all you want to do. But with GridGain, the way that we're set up, you can actually now sort of coalesce all of this down into one group of servers. It becomes your data and compute grid, and you can run your applications on that grid. Now, this is not the only model. I'll show you other models. We can do sort of a client-server model as well. But in terms of evolution, right, to us, this is where we would like to see things go. So all my data is in memory, right? Forget about the disk. I'm not saying we have to get rid of it, but from a performance standpoint, our application doesn't care. It's never going to hit disk. I have this grid, so these grids can talk to each other. Computations can be spread around, right, independent of the fact that each one of these may or may not have a copy. When I say user, I mean your app, right? So this is your app. Each one of these servers may or may not host a copy of your app, but they're all fully participating in the grid. They're all available resources for any distributed computation to store data, etc. And this is horizontally and dynamically scalable, so I can add servers to the grid anytime I want. So in our opinion, this is kind of the ultimate evolution, right? So I coalesce everything together. All data is in memory. Computation is distributed, working on local in-memory data sets. We'll go into this in more detail. But it doesn't get much faster than that, right? If I have a request, I get data locally in parallel on lots of machines, do the crunching there, send the result back to whoever needed it. Doesn't get a lot faster than that. So if we're going to do that, what are some of the things we need to think about? So this is true. This is not specific to GridGain. It's not specific to data grids versus in-memory databases. It's really kind of across the board. So number one, again, just repeating the theme here, performance. I care if it performs, right? First and foremost, that's the goal here. Secondly, scalability. So there's three things: vertical scalability, horizontal scalability, and the ability to increase my scale without using outage windows or without taking downtime. So again, we'll talk more about this, but briefly, horizontally scaling means what you would think. It means I can add servers to my grid at any time and just add capacity, not having to take an outage to do that. And then vertically, in the Java space, as you guys probably know, there are challenges. How much RAM can I use in a single process? So that's something you need to look at. Consistency. So does everybody know what I mean when I say consistency? So what I mean is, if I have a grid of servers, like let's step back to this picture, no, that picture. So if I had a grid of servers, I've only got two here. We have some better diagrams coming out, but we'll use this for the moment. If I ask this server about a particular piece of data, and I ask this other server the same question, what is the latest value of this piece of data? Do I get the same answer? That's consistent. So, I mean, with two, it seems a little silly, but imagine having 500 nodes, right? So do I get a value for a piece of data here on node 10 and do the same thing on node 412? Am I going to get the same answer at any particular instant in time? So obviously that's important. And there are products in this space that will give you strong guarantees about what you're going to get. There are some that give you no guarantees about what you're going to get. And there are some that kind of give you choices and trade-offs. And we'll talk about our approach to those trade-offs. But it's definitely something you want to understand, you want to think about and ask about. Number 4 is persistence. So for storing data in memory, what's everybody's first thought? Anybody? You're going to put all your important business data in memory. What's your first question? What happens when the power, well, crashing or power goes out? Yeah, let's say the power goes out. A little more optimistic, but Obviously, RAM's volatile, right? So again, different products take different approaches. Some say, we assume that whatever you put in this product is not important. If you lose it, big deal. Obviously, that's not our perspective, but there are products like that. Others will ensure that you've got multiple copies of the data in memory. Some will let you optionally go ahead and persist to disk. You can do that synchronously, you can do it asynchronously. There's performance trade-offs. So again, things to think about. And of course, if you keep the existing relational database in the picture, maybe that's the answer. For some people, it would be. Number 5 is transactions. So can I support transactions? Is that important to you? Right? In a traditional database, you can start a transaction and modify 5 different tables, and then it'll either all commit together or it'll roll back if something doesn't succeed, right? Some people need that, some people don't. If you need it, you want to understand if your in-memory product supports that. And last but not least, search or query. So as I mentioned earlier, a lot of the products in this space, outside of Hadoop, which we're going to talk about later, but in the context of in-memory databases and data grids, things like that, either it's going to be a traditional relational model or it's going to be, in most cases, the key-value model. So how do I go find something if I don't know the key in a key-value model? I don't know the key that I'm looking for, right? How do I go find it? So most products will give you some mechanism. It's, again, something you want to understand. How does it work? Is there a search API? Can I write queries? Is it SQL, right? Does that make sense so far? Fairly logical? Okay. Any burning questions at this point before we jump into the next segment? Good. All right. So let me talk a little bit about GridGain and kind of talk about how we address some of these issues and questions. And I guess I should sort of explain, who GridGain is, because we haven't really talked about that. So GridGain, as you can see here, founded in 2007. We are an entirely in-memory focused company, right? And really the vision of our founders was to sort of have a suite or a stack of technologies, to not just do one thing. Like caching is one thing that we can do. It's not all that we do. So they really wanted to sort of build out a platform of different pieces, building blocks, if you will, that are integrated together, but you're not forced to use any of them. There's sort of like a menu of choices and things you can put together to build applications to do the things that you need to do. We've had software in production for over 5 years. We have both open source and enterprise products. And if you put all those together, those start numbers that we're pretty proud of, you can see there, kind of encompass all of that. The use cases that we get involved in. So we've talked a little bit about this already. Slightly different version of the slide that you saw earlier, now with some logos on it. But again, financial has been a huge adopter. We have some very large customers. I'll show you one in a moment in that space. Online and mobile advertising, payment processing, those types of things. E-commerce, obviously. So fairly diverse, but let me highlight one of those. Which is Sberbank. And they are a very large bank in Europe, Russia and Eastern Europe. They had a very, very competitive open tender that we are very pleased to have won with some very, very exacting requirements. So they really put us through the ringer and did a number of different tests. They tested 100 plus terabytes in memory. They tested upwards of 1,000 nodes. And there's one particular test that we really like where they wanted to be able to do 1 billion transactions per second. Now in this case it was essentially writes, but within the context of a transaction. So transactional writes per second, 1 billion. We did that on 10 commodity blades. And aside from being a nice impressive number, this is the other key point here, is that this was pretty inexpensive hardware. In fact, if you wanted, these are standard 1U servers, and if you wanted to get refurbs, you could probably cut that number in half. So a terabyte of memory, 25, 35K, 45 maybe. Pretty surprising. A lot of people really, if you haven't gone and looked at that. Total, yeah. So like 128, gigs or so per server times 10. So with that said, let's talk about what the technology is. So a couple of things I'll explain first. So first of all, we're Java-based software, right? So although we support other languages as consumers or clients were written in Java, so that means we run in a JVM. And the nice thing about that, as many of you probably know, is that you can pretty much run anywhere. You can run on your own hardware, physical hardware. You can run on your own VMs. You can run in the private cloud, in the public cloud, right? Any of those things are fine. So, well, a couple of years ago in open source, they did sort of an experiment with that. Yeah, it didn't really take off a whole lot, but it's possible. So if somebody wants, if somebody wants to revisit some of that, let me know. That could be interesting. So yeah, we're Java-based. And then the other thing, as I mentioned, we love to talk about, and I will talk about how the different pieces fit together and how they can be used together. But please don't misinterpret that as saying that you have to use them together. So again, we have lots of customers that say, I need this piece or that piece. And that's fine. So we work with both. We work with both. Yeah, and I'll kind of explain what we do, how we plug in there, and oh, sorry, I should probably repeat, right? So the question was, do we work with Hadoop 1x or 2x? So yeah, so we'll get to that. What I'm going to do is kind of go in this order, and then I'll come back to Hadoop. So this is kind of the way the product's evolved over time for GridGain, so I think it kind of makes sense to sort of do it in that context. So the first product for us was the high-performance compute. This is where GridGain got its start, and the concept here was to have a powerful, flexible, easy-to-use, configurable framework for building sort of pure distributed compute apps, right? So I have some computational problem, and I want to put 10 or 50 or 100 or maybe even 1,000 nodes of JVMs to work crunching on this particular problem. So as you can imagine, one thing that you have to do first, before you can do anything interesting in terms of a grid, is there's sort of this foundation layer of technology, which we don't show here, but I think it's worth highlighting. It's sort of all the unexciting, but very important engineering work of sort of building a foundation of a functional grid. How do nodes find each other? How do we do load balancing? How do we do high availability? All those kinds of things. Security, authentication, et cetera. So that foundational layer, although its origins sort of begin here in HPC land, now really cut across all the products. And the nice thing is, as we've evolved over the years, and we're on version 6.1 right now, soon to be 6.2, so a lot of major releases, a lot of innovation, but that foundation continues to sort of be improved and hardened and battle tested, if you will. So okay, great. We've got a foundation. We can fire up a grid. They can coordinate. They can work together. I was starting to explain the first piece, which is HPC here. So what do we do? There's a set of APIs, of course, that you're going to code against in the case of HPC. That's the part that you would see as a user, right? So what does it do? So the first thing I'll mention is that we have in that API support for our own concept of MapReduce. And of course, this is fun now when you say MapReduce and everybody thinks Hadoop, and we have a product in that space. But in this context, I'm not talking about Hadoop. I'm talking about the same paradigm, but this is our API around MapReduce. But we also have support for other paradigms. We have messaging in the product. We have support for building RPC-style applications if that's what you want to do. So it's very flexible. There's some pretty cool things in there. I mean, normally you're going to use this to put together, an event-driven application, but we do support scheduling as well. So, even the most event-driven applications typically have background tasks or sort of housekeeping things that need to be scheduled. So we support that. As tasks are executing throughout the grid, you have the ability to share state between those different tasks through a concept of task sessions. As you can imagine, we're going to provide high availability and failover. So it is possible that a job might be on a piece of hardware that fails. We'll move it, of course. And that's where the checkpointing comes in. So if you checkpoint the progress of whatever that task is doing periodically, and if it has to get moved due to hardware failure, it can pick up where it left off. A couple other things I'll mention that I think are pretty cool. So one is the zero deployment technology here. And if you think about this for a minute, let's say I have a grid of, 50, 100 nodes running somewhere in a lab, and I'm going to write code that's going to execute against this grid. It would be a huge pain if every time I write a line of code, I have to compile and build a jar and copy it to 100 machines, and then run it and wait to see what happens, right? So the zero deployment technology is meant to solve that problem, and it means that you can be sitting there writing code in your IDE. You've got your 50 nodes running over here, in your lab, but you're writing code, you're in your IDE, you hit run. Those computations or closures that you create are then sent out dynamically, right? So I don't have to build jars, I don't have to copy the files around. Greatly speeds up the development process. Now you're not forced to do that. Like in production, you might lock it down and say, I want people to have a managed deployment process. That's fine, but you can. One other thing I'll highlight, maybe two things, but the early and late load balancing. So this is another example of kind of thinking about that foundation layer, right? One of the things that we feel is our responsibility is to worry a lot about utilization, to worry about efficiency, to make sure that the resources in the grid are being used to their best advantage. And the early and late load balancing speaks to that. So we essentially have a two-stage process here. The early piece means I do kind of what everybody would do. It's like you create a task, you say to run it, we look at the resources available, find the node that seems to have the most resources free, and we send it over there. But grids are very dynamic, right? So between the time that we've made that decision and we've sent it across, even though that's an extremely short time frame, it could be a couple milliseconds. But things could have changed, right? So maybe I have an app on that server that's suddenly waiting for I/O or some external process. The second stage, the late load balancing, would kick in. Another node, let's say, gets sort of freed up early. He can go, hey, I'm available. Let me look at some other queues and find a job that needs to be done, and I'll pick that up and execute it. So again, I highlight it just to kind of say these are the things we think about, right? Making sure the grid's efficiently utilized. So we have kind of a visual of that, just kind of showing the grid running. We'll talk more about this as we get into the actual data piece. I kind of like this picture, not as pretty as the marketing graphic, and I did it, so I'll take the blame for it not being as pretty. But this is the basic idea, right? So an application sends out a request. This is the MapReduce approach, obviously, right? And I'll also tell you that it's kind of unfortunate. So the time that this was being designed, right, most people hadn't heard of Hadoop, at least outside of Yahoo. And we actually picked the opposite naming, so jobs and tasks versus tasks and jobs. So in our case, it's tasks and jobs, right? So that it gets split out into multiple jobs, sent out to the grid, executed, result comes back, gets aggregated, returned to the caller. And that's what we're doing with the MapReduce type of approach. And then, as I mentioned, the failover, if this guy was supposed to execute here, but that guy's power supply crashes and burns, we'll move that task to another node. So now that I've just shown you a couple of deployment options, let me pause before we talk about the data grid and explain how you can deploy GridGain, because we've actually seen both of these models. So the interesting thing about GridGain is it's sort of a grid of peers, if you will. I hesitate to say peer-to-peer because then people think of things like BitTorrent and you think of like clients communicating with each other. It's not peer-to-peer like that, right? But it's sort of a grid of peers in the sense that all nodes are created equal. Any node can perform any function that's available in the software, but you determine through a config file what any particular node is going to actually be able to do or not do. So when you start a GridGain node, which might be through a shell script, and I don't know if anybody's looked at our software, but you download it, you unzip it, you tweak a config file, run a start script, or you put it in as a dependency in your application and you can start it through a line of code. In either case, you're passing a config file. That config file is going to tell those nodes what they can and can't do. So through that mechanism, you can set up this scenario where I essentially have application servers that would start a grid node that's just going to really act as a client. It's going to forward requests. That's really all it'll do. It's not holding data. It doesn't do computation. It's a client. And then I have another grid of nodes that I'm going to start with those things turned on. It will store data. It will do computations, right? So I can set up a client-server type of model. Or I can do this code-deployed model, which we sort of showed a little bit earlier. And in this situation, I can have a fully featured grid node storing data, doing computations, running side by side with my app, probably on a slightly more powerful app server. And that can either be in two separate processes, especially if you're not Java, it would be two separate processes. Or if you're Java, it could actually run in the same JVM. You may or may not want to do that, but that's, again, a choice. Does that part make sense? Good so far? Okay, so moving on. Back to the big picture. we talked briefly about HPC. Let's move one to the right. The next logical evolutionary step many years ago was to add the Datagrid capability to the HPC. So here, you're already going to kind of see one difference from us. So we came from the HPC space. Right? We didn't come from, let me store data and then figure out how to compute it later. It was compute first. And then storing data in some ways is a logical extension and maybe even easier, although you could debate that. So the Datagrid. What are the characteristics here? So it is a distributed key value store. As we mentioned earlier, keys and values are both objects, so these can be any arbitrary objects. I mean, it could be as simple as integer string, or it could be something much more complex. Your business objects, you know, big hierarchy of collections of collections, you know, that kind of stuff. As I mentioned earlier, to me, the key feature for any data grid is scalability, right? So I mentioned some of the numbers, terabytes of data, 1,000 nodes, etc. Let's talk about that scaling. So if you think about the question that we asked earlier, how do I scale vertically and horizontally? Do I have to take outages to do that, right? So how do we address that question? So we can scale horizontally in the way that I would think you would want any grid to do, right? I just add nodes on the fly while things are running. There's no downtime, there's no outages required to do that. Just add a brick, as they say, right? Add nodes when I need to. Or remove them. If you had extra capacity, you realized you didn't need it, remove it. From the vertical standpoint, if you want to use large amounts of memory in a single process in the Java world, what's the problem that you're going to run into? I'm sure somebody here has run into this, right? Garbage collection, yeah, exactly. So if you try to run, you know, too large of a heap, I think the sweet spot is fairly modest, maybe 6 or 8 gigs. You know, you got some people with a lot of expertise and a lot of tuning might push it 12, 16, you know, maybe a little bit more. But if you try to do more than that, the garbage collection performance is going to kill the performance of the application. You will not meet your SLAs. So the solution there, in our approach, is to have an off-heap storage capability. So we have that. And what that means is we have, I'll go forward and come back. So in a particular node, right, you have your on-heap capability, like any Java application would, and then you have this off-heap store that can be as large as you need. So I can run that 6 or 8 gig heap, keep my GC under control, and then if I want to use 10 or 100 gigs or a terabyte of RAM, whatever you got, you can use that with the off-heap support. And you don't have to worry that that's going to impact your performance. So it scales very, very well. It's very linear, very unlike GC. Next thing, high availability. So I'll talk more about this as we look at some of the diagrams of the data grid. But once we get there, make sure that I come back to that point. The short answer is we keep multiple copies of data in memory. That's configurable, and the failover is automatic. Data consistency, this was another one of our questions, right? So if I have 10 nodes or 100 nodes, do I get the same answer from every node if I ask for the same piece of data at exactly the same moment in time? With us, the answer is yes. Now what you'll see out there, there's products that really cover the spectrum. You know, there's products that give no guarantees, some that will give you a choice. Like I can have the weak or eventual consistency, which basically means that all the nodes will eventually get the right value. But if you ask right after something has changed, there's a window in which you may not get the same answer, right? So that's eventual consistency. And some products may default to that, but then they'll let you turn on a stronger model where you're guaranteed to always get the same answer. But most of those that give you that choice, give you the choice because they can't perform well if you're running the strong consistency. There's a big performance hit. As you can imagine, it's a difficult challenge. There is more work to be done to maintain that consistency. And it's hard to do. Now at GridGain, we've architected from the ground up around the concept of strong consistency. So we believe in that. We think that you need to be able to trust the in-memory data store just as you would your database. So we have an MVCC-based concurrency model where we can deliver the strong performance and also guarantee that consistency. The other question I asked earlier was about query capability, right? So it's key value store. If I know the key, boom, easy, right? Basic operations are things like map operations, right? Get, put, remove. I get something by the key. But if I don't know it, how do I find it? So for us, we have a SQL query layer. So you can write what essentially looks like standard SQL. Has anybody used Hibernate here? You've seen HQL? So you know the concept, right? It looks like SQL. In the case of HQL, you're querying objects. So it's like instead of from table, it's like from object, name, insert name. And in our case, it's the same thing. So it's essentially standard SQL, but in our case, you're selecting from these objects that are in memory or cached. And we actually also have a JDBC driver, so you can get connectivity for applications that only speak SQL. Now, the one thing I'll be clear on is that this is intended for reporting, so search and reporting, right? So it's essentially tools that want to read data, you can read through this interface. A couple of other points with the Datagrid, and we're going to look at some more nice diagrams, which I think are much more interesting than a whole bunch of text. So in our APIs, you have a lot of choice. You have, for most of your operations, a choice between synchronous and asynchronous operations. So, you know, do something and I'll wait for the answer, or do something and then give me a future and tell me when it's done. And even if you do something synchronously, you can decide, do I want to wait until this piece of data is stored in one place? Or if I've configured, let's say, 3 copies, do I want to wait until it's on all 3 places before my call returns? So you have a lot of choices. And the last thing I'll mention is pluggability. So this is another thing that I haven't seen very often with other products and that we feel quite proud of, is there are 14 or 15 different subsystems in our software that are kind of a scenario where rather than us enforcing one particular behavior on you, we'll give you a choice of 2 or 3, and then you can pick one of those. But if you don't like it, there's an interface where if you want to write some Java code, you can implement your own behavior. So that's pretty cool. And they're fairly lightweight interfaces. We call service provider interfaces. So that's well and good. Let's talk about how we actually store the data. How do we handle the high availability and all that good stuff? So there's 3 modes: local, replicated, and partition. So let's talk about what those are. So here's the pretty marketing diagram of the Datagrid. Here's my version that I like. So here we're in that sort of pseudo client server model, right? So I have application servers, they're going to request data. Again, right, keys and values, objects. Those objects could be anything. It could be very simple. It could be a string, a container for XML or JSON, or it could be my business object, you know, big nested hierarchy of stuff. So that's totally up to you. But they're requesting data, right? They may also be issuing compute tasks, but we'll get to that in a minute. You may have other applications connecting into the SQL interface. We're leveraging the heap and off-heap storage. But what are we actually doing here? And then once we've talked through that, then we'll talk about how the traditional database fits in. So what are we doing here? So I'm running a bunch of GridGain nodes. And for us, you have to define these logical stores, right? You can have as many of them as you want. And programmatically, we happen to call those caches, right? So you have a bunch of caches that are going to hold data. And those 3 modes come into play now. So we have, for every cache, you can have local, replicated, or partition. So local would mean it literally lives only on one node, which for that matter could be one of these nodes. You know, that's useful for temporary data, intermediate results, that sort of thing. Not really that commonly used, to be honest, but it's an option. Replicated means that data is going to be stored on every single node. So every node in the grid has a copy of that data. Now, as you can imagine, that's not the most commonly used mode either, because there's a lot of overhead to that. But it is sometimes really useful for smaller reference data sets that any query or any computation would need access to. So what are we usually doing? We're usually doing this partition mode, right? So I define sort of at this layer through configuration these logical caches. Each one of those caches is then broken up into a bunch of buckets or containers. We actually call those partitions, and that's why that mode is called partitions. So any logical cache broken up into a bunch of buckets, those buckets or partitions are then assigned to individual nodes. And that assignment is dynamic. If the topology doesn't change, it's not going to change, you know, randomly, right? But it's dynamic so that the topology can change. So for any given key value pair, we run that key through a consistent and predictable algorithm that happens to also have the knowledge of the topology of the grid. It says this key value pair lands in this partition, and that partition is mapped to this node right here. That's how we know where the data goes. And then for every active partition, there's n number of replicas that you've configured. So do you want 2 copies of the data? Do you want 3 or 4? Or you can turn it off and only have 1. So there'd be an active partition, you know, here, let's say, and then there's a replica partition for that little slice of data somewhere else. guaranteed to be on a different node. But other than the guarantee that these actives and replicas live on different nodes, the distribution is essentially even and random. So that's important, I think, because, again, comparing and contrasting with other products that are out there, you know, some have a sort of a master-slave relationship where you say this node, sort of at the node level, this node backs up this other node. You know, and that's okay, but the problem is if that one node goes down, then you know that other node has taken all the load. So we like our approach better, where you have these, you know, partitions distributed around the grid. You know, it's almost like a RAID 5, right? But with RAM in different servers instead of with disk. So you have a little bit of the primary data, a little bit of the redundancy data on every node. If you lose a node, then every other node just does a little extra work instead of one node doubling up, right? So we think that's a much better scenario to be in.
So your redundancy is like an extra 20% overhead to 200%?
Well, no, I mean, it is 200%, right? So if you say I want 2 copies of data in memory and I'm storing 100 gigs, you'll need 200 gigs of capacity, absolutely. So that is true. And that's why it's configurable, right? So you get to trade, how much capacity versus how much safety. And then the last piece on here, well, I should say one more thing. So if a node goes down, as I said, other nodes do a little bit more work. Essentially all we have to do, if you lose a node, right, we've got copies of those slices of data in many places. The ones that were replicas sort of flip the switch and become active. And then all we need to do is create some new replicas somewhere. If you add new nodes, we'll do it there. If you don't, we'll start creating those on existing machines. There's a configurable delay if you want to wait a certain period of time before we do that. And we can dive deeper into that. But at a high level, that's kind of what happens. And then the last thing we should talk about is the database, right? So, you know, in most cases, we're not going in and having people say, I want to get rid of my Oracle database, I want to get rid of my SQL Server, MySQL, you know. You don't, in 90% of all cases, right? You have ETL processes built around that, you have reporting built around that, you have backup and recovery built around that. So you typically want to keep those things in place. But what you want to do is sort of decouple your application from the dependency on that performance level, right? So we talk about a hot set of data. You have a large amount of data in your database probably, and when we get to the Hadoop piece, you know, it's pretty much guaranteed you have a large amount of data in Hadoop. So what is important, right? It's if I have 5 or 10 or 15 years of data in my database, do I need all of it all the time? You know, probably not. It's probably this month or this quarter or this year, something like that, that your folks are going to hit all the time, day in and day out. So we lost that data into the grid, and then applications that we build that need to consume that data, or things that can talk SQL, can get that data extremely rapidly. I can scale the infrastructure that supports that data independently of my database, decouple myself from that performance SLA. So the last piece of it, well, so again, let me pause, take a breath. Questions on that? Making sense still? So the last piece of the puzzle, let's bring compute to the data. When we bring the compute to the data, what does it look like? Well, going back to our map-reduce paradigm, right now I have data sets in memory on lots of different nodes. If I need to do some computations against those data sets, right? So in this case, I'm saying I have a task that needs data set B, D, and E, which happens to live on these 3 nodes. We break it out into those 3 sub-jobs, do that work on each node in parallel on local data in memory, send the result back. Scales extremely well. So again, if we contrast to sort of the traditional model we talked about earlier, right, where I go out to some grid, ship data across the network, do all the work on the app server, and then as far as I'm concerned, I may or may not ever need that data again. We can now, instead of moving data across the wire, move computation across the wire to the data, operate in parallel, do the compute in the grid, and just send the results back. So if your data sets are small, that model on the left probably doesn't really hurt you too much because you're not sending that much data across the network to begin with. But as you scale, as the data sets grow, this becomes a big problem. So if you can move to a model with very little data movement, do the compute in parallel, it makes a ton of sense. So one more piece, and I'll try to speed it up because I think we're running a little long. We have still 7:45 is what we budgeted, right? Okay. So, streaming. Streaming is kind of the third piece of this little trifecta here. The streaming component we've added to the product. It's not brand new for us anymore. It's been around a little while, but one of the more recent additions. Because it's a use case we're seeing more and more of. And I talked about that customer 360 view and data sources coming in from all sides. That's sort of an emerging streaming use case. But again, you have traditional use cases for folks that are in financial. You know, got market data feeds, or if you're a social media company, obviously you have streaming data. But whatever the use case, we think that there are essentially two things that you have to be able to do to process streaming data. Number one, keep up with it. And then number two, extract intelligence from it. So under the heading of keep up with it, I have to build this horizontally scalable layer that can process events in real time, an infrastructure that I can add nodes to whenever I need to, because I can't slow down the stream, I can't stop it, I just have to keep up. And then once I've done that, I have sort of a CEP type of a problem, right? How do I look at these streams and do queries continually to find the things that I want to find? So that's what our streaming product does. It has two pieces. There's a workflow layer, and this is done in a combination of code and configuration. You define any number of stages that you want. Those stages run any arbitrary code that you want, but it's essentially the infrastructure that lets you create the workflow and ensures that it runs in the grid in an efficient and scalable and resilient fashion. Typically what you're doing in these workflows is some kind of data cleanup, processing, cleansing, right? I'm adding metadata, I'm filtering, whatever the case may be. And then at the end I'm persisting it somewhere. We would probably say let's persist it to the data grid, perhaps with a write behind to the database, which I'm realizing I don't know if we explained. So real quickly, you can read through, write through, or write behind to a database. So the write through, write behind is just synchronous or asynchronous. So at the end of a workflow, you've cleaned up the data, you might persist it to the data grid, you might have that write behind where those events will queue up and get written to the database in batches, and it's all configurable how that behaves. But we can absorb the events very rapidly and then sort of trickle them down to the database as needed as we can support whatever performance is available. And then once I'm doing that, so that's all well and good, and you could use just that piece. But if you then want to query these streams, we have this concept of data windows. Typically these are time bound, so I want to look at the last hour of data, last 15 minutes of data, last day, whatever it is. And you can have multiples, right? So have all these different windows. Events come in, they're evaluated against criteria that you've defined. They're indexed, they can be queried either continually or on an ad hoc basis. So if you kind of put that together, this is the way I like to sort of visualize it. You know, you have these event streams, you probably have load balancers and things that we're not showing, but assume all of that. It lands on a server where all these servers are identical, and I can scale out, processing these event streams. We're running GridGain nodes. Within those, these workflows are happening. Again, multiple workflows if you want, conditional logic if you want or not. Cleaning them up and then dropping those events into windows. I'm only showing one, but again, you can have a whole bunch. You can imagine events coming in on the left, sort of being pushed out on the right over time. And then any queries that I've defined, you know, these incoming events are going to be evaluated again. And as I mentioned earlier, you can also go in and write queries ad hoc. Those windows get indexed, so that's easy to do. So that is sort of the core platform. You can imagine how these things fit really well together, right? I've got data coming in, I use the streaming APIs to process it, I store it in the data grid, and once it's there, all the HPC stuff is available for free. The APIs are there, I can use them, I can do distributed queries. Like even if you're just writing a SQL query, it's still sort of using that parallelization infrastructure. But you can of course create your own tasks and things that you want to do in parallel. So with that said, and I should mention too, again, highlights that we support not only Java and Scala, which we use both in the product, but C++, .NET as clients, and we have a REST interface, which can be Memcached compliant. So if you're dealing with the data grid and you're in some language that has a Memcached client that's not Java, C++, or C#, you can interoperate there as well. So that brings us to Hadoop. Any questions on the data grid stuff?
So what's next is the data stream sort of plugging in Kafka and data?
So, I mean, typically that's all custom. So, I mean, it'd be kind of use case specific. It's not that there's necessarily a library of pre-built connectors, although that's something that we've talked about. If you have interest in one in particular, let me know. Yeah, absolutely.
And running those support to what's called transactions, if something goes wrong, play back or
So in the context of Datagrid, and that's one thing I didn't mention, we do support transactions. So we have our own transaction API. If you want to get fancy and do distributed transactions, we can participate. You know, we're not, in that context, we wouldn't be a coordinator, but we can be a participant resource in a distributed transaction. In the context of streaming, I don't know that we have any specific semantics that are different in terms of transactions, but any operations that involve the data grid, you can use that same transaction API. Sure. Right. So it's something, you know, again, that you could build. I mean, there's nothing out of the box to sort of replay. But like we have a concept of distributed queues, for example. So if you wanted to, for safety, you could put events initially into a queue and then process them through the series of steps. And if something goes wrong, you go back to the queue. So I mean, you could get there. A little bit of work, but you could get there. Any other questions? New Hadoop? Okay. Mm-hmm. Sure.
How would the in-memory features of Replication make this faster?
So obviously everything is use case dependent, right? And it depends on the data and your usage patterns and all that kind of good stuff. I can give you some anecdotes and some rules of thumb though. Anecdotally, traditionally, now things have changed a little bit this year with the big three vendors, you know, Oracle, Microsoft, and SAP. But you know, databases in theory have sort of had caching for years. They've had the ability to, you know, turn on caching and use memory on the box. What we've seen historically, and the reason really that these grid products have flourished, is that although the concept is there in theory, in practice it just doesn't work. It isn't that much faster. I've had the experience, and I've had a lot of customers that have tried to scale up, you know, SQL Server or MySQL. I don't run into Postgres as much, so I won't claim to be a Postgres expert. But you know, give it as much memory, give it enough memory that can hold everything, and it still doesn't come close to what you can get out of the data grid. Now, there's a couple of reasons probably for that. I mean, obviously, I don't know what they're doing in terms of internal architecture that may or may not be optimal. But there are a couple of things that are different. So, you know, in the case of just can I make my database faster, right? And again, there have been movements from the big three where they're taking in-memory more seriously and they're doing better, I think, than they ever have at this. Yeah, you can make it faster, but you're still going across the network. You're still getting relational data. You're still marshalling it into objects. You're still, you know, probably discarding that data on the application server after you've used it and then repeating the process the next time you need it. So when you move to a data grid approach, especially one with near cache, which we didn't talk about, but you know, if you're a Java application and you're using our API as sort of a client, you can turn on a near cache where we hold some data locally. It's not the primary, it'll never be the primary copy of the data. It's data that can disappear if it needs to and doesn't hurt anything. But we can keep some data locally right next to the app. So we can co-locate the data with the app in the native format. You avoid the trip across the network entirely as well. You know, that is a significant difference. So for rules of thumb, I would say, in my experience, you know, if you have a near cache like that and you have data that's there in the heap that you can get to through a caching API, you know, you're talking nanoseconds to get to that data. With an off-heap store, there's a serialization step, so anytime you leave the heap, whether it's to go into off-heap or to go to another box, you have to serialize. Most everybody I know, and certainly we do, uses optimized custom serializers to make that as fast as it can be. So probably a microsecond or two to get to that off-heap data. Still tremendously fast. If you have to go across the network, now you're talking milliseconds. If it's going across to a data grid that has data in memory, probably 2, 3, 4 milliseconds. To a database, typically, you know, again, everybody's different. You can throw more hardware at it, but, you know, I've seen 250 milliseconds. Seconds sometimes, you know, if it's big queries. So it's pretty significant. Like in my experience, you know, I've seen situations where Well, first of all, I should also say, if you're not getting 5x, 10x performance improvement with one of these kind of products, you're doing something wrong, in my opinion. It should be at least that big. It should be significant. And I've seen situations where traditional architecture, lots of app servers, try to scale up the database really big, versus going to a Datagrid, the ability to support, for example, 5 times more users on the same hardware, just because you've cut out so much latency and you're not waiting for data access. So, short answer, it should be dramatic. It should be a significant difference. But every use case is different. We always say, let's understand your data, let's see how you're using it, let's come up with a test that will show us what we can achieve in that situation. So, good question. Let's talk about Hadoop. So there was a show of hands. So who was using Hadoop? Okay, great. Is it Hadoop 1 or 2? And somebody already asked that. 2? Okay, yes. You guys are on the curve. Excellent work. Hadoop is an interesting world right now, right? Tons of excitement and innovation, but I kind of see it fragmenting almost even more. So we were at Hadoop Summit and we were at Spark Summit, and you kind of see Hortonworks going, we've solved everything and here's the answer, and then you kind of saw Cloudera at the Spark Summit going, not so fast, we have a totally different idea. Come talk to me about that later. But at any rate, like everybody, right? We saw a tremendous opportunity in Hadoop. And kind of the funny thing for us about Hadoop is it's popularized this idea of let's take compute to the data, right? At the time when GridGain was coming about, as I mentioned, nobody had really heard of Hadoop unless you worked at Yahoo. So this was kind of a foreign concept, and we used to have to kind of, help people understand that this is a good idea. Now with Hadoop, it's kind of like, oh yeah, compute to the data. That makes perfect sense. Everybody should do that. Now, of course, in the case of Hadoop, certainly in a version 1 world, you're talking about data that's all on disk. So we wanted to bring some of our expertise into that Hadoop space. The way that it made sense to us to do that was to plug in at the file system level. So this is what we've done. We've taken our existing Datagrid technology. So we didn't build something from the ground up that we dreamed up 6 months ago or something like that. This is the Datagrid we've been working on for years and years. There is a new piece, which is just a file system layer that sits on top of that. And we present that to Hadoop. It implements the HDFS API, essentially, so it looks and acts like HDFS. And it stores data in memory, right? So that's the big deal. You can use it in one of 2 different ways. You can use it standalone, where we essentially have no data on disk. And that's cool in theory if you're building a small Hadoop cluster just for some pure performance application. But in most cases, again, just like we don't get rid of the traditional database, you don't want to get rid of the disk completely. You have lots of data there. Some of it's important, some of it's not. You take the important data, put that in the in-memory file system, and we essentially become sort of an intelligent caching layer for HDFS. So you configure, again, file system, right? So files, directories. What files, directories do you want to cache? What do you not? As you request data, if it's something you told us not to cache, we just pass that call back to the underlying HDFS file system. And if it's data you've told us to cache, we'll put it into memory. We store it at the block level. We'll use up as much space as you give us. So you can imagine this process that's holding that memory is running on each Hadoop data node. So there's another JVM with an instance of GridGain there. And then once that memory is full, we have intelligent eviction algorithms, as you would expect. So we get rid of your least frequently used stuff, keep the hottest stuff. And if we need it later, we just go back to HDFS and get it. There is, a couple other quick points. So the nice thing about plugging in as a file system is that does mean that we can support either 1 or 2 versions of Hadoop, any of the major distros. So it's pretty plug and play, right? You just run that process on the data nodes, drop a couple jars into the driver for the file system, and then in your config, either globally or on a job-by-job basis, you point to this GGFS file system instead of HDFS. And then GGFS internally knows how to talk back to HDFS. So of course, you have to configure that. But you pretty much drop it in, put data in memory, and go. And that's kind of the concept. Simple to plug in and play. You can see even on some pretty trivial benchmarks, creating files, random access, that sort of thing, pretty significant speed-ups from that. And then there's this other piece, which has actually changed, and we haven't even had time to update these graphics yet because this is coming out in our 6.2 release of GridGain, which is in a sort of a RC preview right now. But let me explain what it is, and then I'll explain what's changing. So we have this in-memory MapReduce concept. So one of the nice things, sort of the things you get for free, sort of the side effect of the way we built this, right? It's the in-memory file system layer on top of the data grid. If you rewind to, you know, earlier in the presentation, that data grid had the HPC stuff built in. So once the data is in the data grid, you gain the ability to use our MapReduce API to go work against that data. The obvious question is, why would I want to do that, right? So again, in the context of Hadoop 1, and then I'll explain how it's a little different in 2, it's easier. But in the context of Hadoop 1, what we found in testing with our prospects and customers is that there is a lot of inherent overhead in the MapReduce framework itself. And I mean, and we've seen this in this space, as a lot of people, particularly in trying to tackle the SQL query problem, are kind of going around it completely, right? Now, this overhead in MapReduce may not bother you if your jobs take an hour to run, right? The fact that it probably takes 30 seconds to spin a job up because these processes have to communicate and ultimately a new JVM is going to be spun up and all that stuff. You know, again, if your job takes an hour, you don't really care. But what if you want to do something in real time? What if you want a job to run that only takes 2 seconds, but you have to wait 30 for it to start? That's not very cool. So we can solve that problem through the use of our MapReduce API. Now in Hadoop 1, you had to write some code to do this. That's the piece that's going to go away in a minute. But in that context, you'd have a GridGain client as part of your application as well as your Hadoop client. And then if you need to do MapReduce in sub-second timeframes, you issue that MapReduce request through our API. It communicates directly to these data nodes. And we don't have to consult external processes. We don't have to spin up new processes or new JVMs. This connection is always on, single socket connection to each data node. So that's how you can get to sub-second latencies for MapReduce. Now this doesn't mean that any of this goes away. This can coexist. You know, all your jobs may not need this level of performance. Maybe this is 90% of your jobs. They keep running. They use the in-memory file system. All that data ends up on disk. For the other small percentage, you can use our API. It all coexists, right? It all ends up back in HDFS. Are you talking? I missed the first part of the question. Right, okay. So when the output, let me repeat that for the... Right, so if you're using, the question was, in traditional Hadoop in the map step, those, what are typically intermediate results would be written to disk, right? Is that the same for us? So no, we certainly don't write it to disk. This is assuming you're using our API, then those results are entirely in memory, even the intermediate results. And then when you're writing it back to GGFS, because this is very granular, you could write it into a directory that's pure memory, or you could write it into a directory that's backed by HDFS, and that could be sync or async. So that's pretty cool. What changes in Hadoop 2 is the need to use our API goes away. So in Hadoop 2, the actual implementation of MapReduce is pluggable. So we've been able to plug our MapReduce under the standard API, which is pretty cool. I'm still learning about it myself because, like I said, this is just in preview now and it's about to come out. So if you're really super interested in that, make sure you got our contact information. We'll be sure to follow up as we get more details. But the cool part is you can get that sub-second type of execution using the standard API, so you don't have to change the code. That's the big deal. Last but not least, and I think we're just about right on time, I would be remiss if I didn't mention a couple of final points. Number one, something we're super proud of, and I really probably should have had it on the earlier slide, where I said if you're looking at any of these products in this space, what are the things you would think about? Management and monitoring, to me, is huge. You know, I've been in IT 15 or some odd more years, worked with a lot of enterprise software. I'm sure you guys are the same way. One thing that's always true for me is, you know, when I get something installed, I want to see what's going on. I want to understand how it's performing, be able to dig around and understand what's going on in the system and do some management. So we've put a lot of work into our tool for that, which is called Visor, and it can manage every product that we've talked about today. There are panels for just about everything, way more than I could show here, even with these pretty small screenshots, so I apologize for that. But the first thing you would see when you launch the tool is a dashboard. As you can imagine, that dashboard would show you sort of key performance metrics. It shows you all the nodes in the grid. You can see configuration information. You can drill in and search GridGain event logs, start, stop, and restart nodes, all that good stuff. But more importantly, there's different panels for all this different functionality. So if I'm using streaming, which is this guy, you see all these streamers and stages that you have defined, and performance, latency, throughput, information for that stuff. If I was using HPC APIs to run tasks, I'd see where those tasks are running in the grid, and I could pause things and drill in if I needed to. If I'm using the Datagrid, I'd see all those data stores or caches. How big are they? How many objects? How much resources utilized by each one? What are the hit ratios? So how is the data utilized? And I can in fact write SQL queries into that data through Visor. And in the case of Hadoop, one of my favorite pieces is we have an HDFS/GGFS profiler, so you can see the performance on a file-by-file basis on the HDFS file system or the GGFS file system. Great. So is that question in the context of Hadoop or in the context of the Datagrid? Okay. So, well, we can try to briefly answer both. In the context of the Datagrid, right, so it comes down to that partition model 90% of the time is what we're using. So there's one active partition for any given piece of data that is essentially the master for that piece of data. But again, keep in mind, these are tiny slices on lots of different nodes. It's not that one node is the master, but that there is a master partition for this piece of data. So sort of the responsibility for ensuring consistency lives with the node that owns that active partition. So if you want to get deeper into the actual mechanisms, please set up a call and we can kind of drill in a little bit deeper. In the context of Hadoop, like I said, we're essentially calling HDFS through the standard API when we talk to it. So if it's something you give us, you write something in a directory that is configured to be in memory with HDFS backing, right? It's essentially the same process as standard Hadoop. It gets written to a particular node in memory, and then because we're running on all data nodes, we're preserving that same data locality. We're just going to issue a call through the HDFS API, write this block. So, it should not feel any different from sort of standard Hadoop. Hopefully that helps. Other questions? So far, so good? Okay. So last couple of points. As we wrap up here, obviously would love to hear a little bit about some of your use cases. Please feel free, obviously stay for the raffle, and feel free to talk a little bit about things that are interesting to you or things that you're working on or wondering about. We certainly would love for you to try out the software. We do have both enterprise and open source versions, so I just wanted to very quickly explain the difference. Our model around open source is, we have these core projects. Every bit of functionality we talked about today, that core functionality is available in open source. But what we do is we add features to the enterprise. So it's the high availability, security, robustness, and the management, all that kind of stuff that makes it enterprise ready, if you will. And that is, what we actually sell subscriptions for. So feel free to play around with the open source. Feel free to play around with the enterprise. There's free trials, so you can get all the functionality totally unlimited, other than, as you can imagine, it's time bound. What do you get with enterprise that you don't get with open source? Very quickly, it's this list. So the Visor tool, we already talked about that. That's an enterprise tool. We may make Visor available in some limited form in open source. TBD, stay tuned on that one. A few other features that I think are interesting. The local restartable store, this gives you the ability to have a local disk backup of whatever data is in memory. So if you're not in a situation where you have a backing relational database, or even if you are, but you want to be able to recover without hammering that relational database to load data into cache, you can have a local store that will give you the ability to just read from a local disk in the event of like a complete outage or a scheduled outage, right? Faster recovery, basically. Data center replication, if you run in multiple data centers and you need to run multiple grids, keep them in sync. We have an enterprise feature for that. There's some robustness stuff, like in, I don't know if you guys have heard of the split brain problem in a grid where this part of the grid and this other part of the grid stop having the ability to talk to each other. What you don't want to happen, the split brain, is that both grids think they're the only one and they're the master. So I'll accept data from the people that are talking to me, and I'll accept data from the people that are talking to me, and what you end up with is drift, right? So these become two different data sets. And unfortunately, both data sets are valid from some point of view. You don't want that, so we can detect that situation. We can prevent it through configurable rules. So you can say, if you can, it essentially comes down to other resources that are available or not. If you can connect to this database, if you can ping this router or talk to this web server or whatever, FTP server, etc., then you are the good segment. So you succeed on these checks, you're the good segment. You keep running, keep allowing people to change data, and then the other segment says, ooh, I'm not the good segment. You know, I'm not going to let people change data. Because that would be something we don't want. There's security features in terms of authenticating both grid nodes and clients. There's the ability to do rolling production updates, which again, I think, you know, in any enterprise scenario I've been in, it's something you want to do. You know, I have 50 nodes, I take out a couple, they were on version 601, I put them on 602, I put it back in. At that point, I'm running both 601 and 602, right? So we support that in enterprise, we don't on open source. And last but not least, of course, is our support, right? So support comes with the enterprise licensing, unlimited tickets, the phone calls, the web meetings, on-site if necessary, whatever we have to do to resolve any issues that you have. And of course, your ability to get consulting and to get indemnification from us. So that kind of summarizes all of that. And certainly if you're intrigued by one of those features, come grab me and I can talk a little bit more about them. But that is essentially all the stuff. So thank you guys for hanging in there. It's a lot of material. And we do have a few more minutes for Q&A, I believe. How are we doing? Okay. If necessary. If not, we'll have more pizza and more sodas and we'll give away.
If anybody has not signed in for the raffle, please do that because it's about to start getting crunchy. Very good. Okay.
Any burning questions?
Can you talk about how GridGain differs from some of the other in-memory, including something like Partition?
Sure. So I mean, you can kind of throw some of these in some broad categories, and that would probably be fun to create a slide for too. So you have the products that sort of came out of the traditional distributed caching space, which is, you know, similar to us, although I explained we actually came from the distributed compute side and sort of added all that data storage stuff. So that's kind of one bucket, right? These in-memory data grids is what the analysts like to call them, and most of us vendors are okay with that term. You know, varying models around consistency, varying levels of support for things like SQL and how they handle high availability, all those things are different. But, you know, broad structures are kind of similar. Then you have sort of the pure in-memory databases, things like MemSQL or VaultDB, where it's kind of like, we're just going to re-architect a relational database, but we're going to base it on in-memory storage. You know, and that's really for somebody that is in a situation where I have to just drop in something new to replace my database. And of course, that's where Oracle and Microsoft and SAP don't want to lose that business, of course, so they're in Oracle 12c, or SAP HANA actually, of course, forced everybody's hand. That really went first, and then 12c and SQL Server 2014, you know, where they're building more in-memory capabilities in there. Obviously, there's a price difference between the incumbents and the newcomers. Then you have sort of like your pure analytic databases that are really kind of targeting the BI data warehouse market, and then even some of those BI vendors will have sort of their own hybrid disk and memory storage capability for the kind of cubes that drive the dashboards. Some of them, other products plug in behind. Some of them sort of have their own storage. Although a few of them are quite good. I mean, to me, it's kind of like, I'd rather the BI vendor just kind of focus on that visual stuff. And I get that from them, and I get the product from somebody that knows data storage and is really good at that piece. You know, and then in the Hadoop space, and especially with Spark, now you have a lot of things kind of blurring the lines. Like at Spark Summit, I saw an analytical tool where they're doing the visualizations, but they're doing all the compute on Spark. That's very interesting. You know, there's a lot of overlap, I think. It's kind of what makes it a fun space, but again, I think as a consumer, it makes it a very confusing space, and you have a lot of different options and things that you have to do. Does that sort of cover the thought pattern? Any other questions? Oh, okay. Sure, yeah. So kind of the end result of those continuous queries and where it sort of becomes that CEP use case is you essentially get a callback, right? So if we find something that matches one of those continuous queries, you essentially get a callback. So you can execute arbitrary code, which means you could, fire off some distributed computation, which might involve a transaction in the data grid, or you could issue a query that might involve a transaction from the database standpoint. Or it could just be you notify somebody, you put it on a dashboard, or move a record into a reporting table, whatever the case may be, depending on how vital it is, I guess, that somebody sees that right now. So it's for the most part something that you would implement. The only sort of alerting type thing we do have in Visor an ability to set some thresholds in terms of what's a functioning grid mean to you, this many nodes, this much available memory, CPU cycles, etc. And we can sort of notify you if those criteria are not met. But in the context of streaming, yeah, we don't do sort of the notification, although you can easily build that with the building blocks that are there. Any use cases that you guys are thinking about that you deal with? Mm-hmm. Mm-hmm. Right. So that's a lovely question, because one of the great things about this particular product is that there's so many different ways to do things. It can be the great thing and also sometimes a challenge. Well, I could do 3 different things, so which one should I do? The nice thing about that key value model, I've seen all different incarnations of this. You can set up a model that looks very much like something that you would do in a relational database, which might involve like a star schema or snowflake schema or something like that. Because you can kind of imagine a cache sort of represents a table, and whatever I put in that cache is like just a plain object that has exactly the same properties that that table would have columns. So you can set up essentially, a table to cache sort of one-to-one relationship. And then if your goal is to sort of run SQL queries, since we have that SQL support, you can do that. And in our product, you can join across caches. There are some considerations about how you store the data. SQL in parallel is a little different than SQL in a monolithic system. But we could delve into that if necessary. But you could essentially mirror what you're doing, in a traditional database. On the other hand, to your point, because it's a very flexible structure, is that really the best option? Maybe let's go back to the beginning. What are these things that are coming in? Do I want to look at them as a stream? I could use the streaming APIs to sort of process those events, put them into windows. Let's say it's a 5-minute window, and at the end of that window I create an aggregate and I store that, so I have an object that represents that 5-minute aggregate. And then I could, instead of doing SQL, do sort of a MapReduce task to go out and find all the 5-minute aggregates that are chunked out on these different nodes and compute the answer to some question that I want, in parallel. So both are valid, and you could probably come up with 2 or 3 additional approaches if you thought about it. So I guess what the discussion usually comes down to is, are we building something sort of from the ground up, new greenfield, new architecture? If you're doing that, then I would really think about sort of using the streaming APIs and using the MapReduce concept and all that other good stuff. If it's more of a situation where it's kind of like I have it all working in a relational database and I'm willing to make some changes to get the performance that I need, but I don't necessarily want to start over and rethink the whole thing, then you might kind of go to that first approach where it's more sort of modeled after the traditional structure. Good questions. Anything else? Good. I think we're pretty much on time. So again, I thank you guys for coming and for hanging out through all of that. And hopefully Cordero's ready to do our drawing over there, and I'm going to turn it back over to him.
Given that nobody is really alive and we're getting in, I promise to still So, let's give you the standard disclaimer for all lottery drawings. What we use is a website called random.org, and that is going to give me a random sequence, if you will, of numbers of everybody that signed up. And we will pick that number. I will tell you who that is. If that person's here, you're a winner.
And if you haven't looked at this, it's really interesting. They use like some kind of atmospheric noise or something to generate true randomness. It's pretty awesome. I only learned about it recently. I'm like, this is the coolest idea.
Okay. So let's see here. Lucky number 22, which is Carrie Miller. Right. There you are. So that concludes our presentation. I know that, the time here in the building, you guys like to see that we're plenty of drinks over there. You guys pour through the pizza already. Just want to say thanks again. Hopefully it was informative to you. Like I said, if there's any other questions you have, or you'd like to talk more about things, or maybe somebody else you might know, you think you want to push them to hear more about the in-memory technologies, my information's there. I have some business card on the desk and whatever. Again, thank you guys for coming, and Marcus, I'll say that over to you. Thank you for your rotation.
I want to remind everybody, you are all invited to the Rocky Mountain High Performance Computing Symposium up in Boulder. I think it's August 12th through the 13th. We're going to have a panel on the future of high-performance computing software. Also, our next event will be at Oracle, hopefully August 27th. So thank you so much for coming, and I invite you to stick around, talk with Mac, talk with Cordell, just network amongst each other, and you all have a wonderful evening. Thank you again for coming.